Welcome back to episode 25 of the Quantum Science Seminar, which will be about dark matter searches today. If you have any questions, please send us your questions to quantumscienceseminar@gmail.com or use the YouTube live chat at the right or at the bottom of the screen. If you'd like to join us for a discussion with today's speaker after the talk, please use the Zoom link that I will post in the YouTube chat at the end of the talk. Please also note there is, as usual, a 30-second time delay between what you see on YouTube and what we do here. And with that, I would like to hand over to Ofer, who will introduce our speaker today.
Thank you, Sebastian. It's a pleasure for me to introduce today's speaker, Professor Marianna Safronova. Professor Safronova obtained her bachelor and master's degree in Moscow State University and received her PhD in physics from the University of Notre Dame. She worked at NIST for a postdoc and joined the University of Delaware as a faculty member in 2003. She is currently a professor in Delaware and an adjunct fellow at the Joint Quantum Institute of NIST and the University of Maryland. Professor Safronova is a fellow of the American Physical Society. Her research interests include fundamental symmetries and high-precision calculations of atomic structure and dynamics, with applications ranging from atomic clocks and quantum computing to searches of beyond standard model physics and variations in fundamental constants. She is blessed with the unique ability to connect her knowledge and special theoretical expertise with practical experimental considerations and to put it all in the context of the bigger picture. And on top of all that, she is also an enthusiastic scuba diver and kite surfer. So without further ado, it is a pleasure to host Professor Safronova today, who will talk about dark matter searches with atomic and nuclear clocks. Marianna, thank you for coming. The stage is yours.
Thank you so much for the invitation. It's a pleasure to give a talk at this excellent virtual seminar. And I will talk about the dark matter searches with atomic and nuclear clocks. And at the end of the talk, I will also talk about the recent progress, which was in atomic structure. So first, why dark matter? Okay. Just a moment. Okay. Dark matter is one of the biggest puzzles in our universe. And the dark matter is not a small effect. The dark matter and dark energy are the largest constituents in energy and matter domain in our universe. Essentially, we don't know what most of the universe is. And those blank spaces for dark matter and dark energy are essentially labels for two what we believe to be different effects. And we don't know actually what causes either dark matter effects or the dark energy. We are pretty sure those are two different things. And if you talk just about matter domain, for example, if you talk about our galaxy, if you talk about our universe matter composition, the dark matter is 85% of all matter. So if you really don't know, not just this abstract things that we don't know what universe is made of, we really don't know what our galaxy is made of. So there is 85% or more of matter in our galaxy, which we don't know what that actually is. And the first question is, why do we think that is actually something we don't know? We have our standard model, and now we nicely found all of the particles of the standard model, including the Higgs. Why could they not be dark matter? Well, let's see, photon. Well, that's clearly not dark. Then all of those quarks, gluons, electrons coupled to plasma, not dark either. All of those decay too quickly. And that's actually one main point. The dark matter has to be either stable or it has to be very long-lived. And the question, why? Well, because it must have been produced at the time just after the Big Bang, and it has to be still here. At least most of it has to be still here. So it haven't decayed so far, so it has to be very long-lived. And the neutrinos are technically dark, but they're too hot. So they could really not function as the cold dark matter to make the universe appear as it is. So we have to have some sort of at least one new particle. And before I start talking about dark matter, I want to talk a little bit about other beyond the standard model effects. And as you can see, actually, most of those can actually be sourced by dark matter. First, many theories beyond the standard model, which we try to actually invent to explain some of the problems standard model have, all of those proposed solutions involve new particles. Those particles can be heavy, or those particles can be very light. For example, also violations of fundamental symmetries, variations of fundamental constants, violations of the equivalence principle, they can all be sourced by new particles. And just to make sure that we understand, if we have new particles, those dark matter particles or any other new particles cannot couple to the standard model particle via usual 4 interactions, well, except gravity. So, but they cannot couple as a electromagnetic strong or weak interactions. So not only we have to have new particles, we have to have new mediators, new forces. So search for new forces is essentially also search for dark matter. We don't know whether those new particles contribute significantly to dark matter or they do not. So when we say we search for dark matter, just let's understand we're searching for some unknown new particles. And they could be partially dark matter, or all of that could be dark matter. Therefore, most of the searches beyond the standard model, with the exception of some general relativity searches tied in just to gravity, they're related to the dark matter, dark sector searches. And today we'll talk about atomic and nuclear clock as dark matter detectors. And I would like to show one slide. I have the whole talk about it, but here I'll show just one slide. How do we actually know that dark matter exists? So it only so far interacts gravitationally with us. And you may have heard about the rotation curves of the galaxies or gravitational lensing, but one of the really extraordinary evidence for the dark matter comes from the CMB, from the cosmic microwave background picture. And you may have seen this picture taken by the Planck satellite. And this picture is taken, essentially we see the universe at 400,000 years after the Big Bang, at a redshift of 1100. And what the CMB map shows us from the irregularities between the cold and hot spots, that over densities, meaning the extra or not enough density relative to actual density. So those over densities were not more than 10 to the minus 4 at that time. So the concentrations of matter were very small, not exceeding 10 to the minus 4. And it turns out to be that without dark matter, it's just not possible to propagate the CMB picture and get our galaxies. Because if you do that, then for a very long time, the scaling is going to be of those over densities would be approximately linear. So if you multiply 10 to the minus 4 to 1100, this propagation of the over densities with time should be about linear, as long as over densities are small. And starting from 10 to the minus 4 and multiplying by 1100, that's still small now. So according to the CMB, if we didn't have any dark matter, then we would not have galaxies by now. So it's not possible to get the large structure of the universe without the dark matter. And this is one of the really very convincing arguments. And we see the evidence of dark matter at all of the astronomical scales. What do we actually know about the dark matter? Well, the most important part, we don't know what its mass is. What we do know, we know its density. So we know approximately what's the density of dark matter in Milky Way. And well, in high energy units, this is 0.3 GeV per centimeter squared, which is kind of fairly abstract thing. Okay, the equivalent of the dark matter mass, it's about 1 atom of hydrogen per a few cubic centimeters. So you see, at the scale of the solar system, we actually have less dark matter, substantially less dark matter, of course, but many, many orders of magnitude than normal matter. That's why we don't see dark matter effects in the motion of planets. We do, however, see dark matter effects already at the motion of the stars around the galactic center. We know the density, but we don't know either its mass or its interaction with the standard model, the non-gravitational interaction with the standard model. So if you just abstractly think, okay, which masses can we have? On a very light scale, as you see, we have about this 10 to the minus 22 electron volt, and that's not exact bound. It could be 10 to the minus 24, 25, depending how much your specific dark matter particle contribute to dark matter. That limit essentially comes from the fact that dark matter have to bind the smallest dwarf galaxies. So there has to be a relation between the de Broglie wavelengths of dark matter to the smallest existing galaxies which we observe. And on the large scale, if you're talking that dark matter is actually a particle, on this large scale, it's a Planck mass. Because what is a Planck mass? If you have a particle which is heavier than the Planck's mass, then your particle becomes a black hole. So this is also not a really good dark matter scenario here. So we have about from 10 to the minus 22 eV to more than 60 orders of magnitude of dark matter, just if it's a particle. If it's a composite, then of course you have all the other different mass scales as well. And you may have heard about those WIMPs. So here is this WIMP city, which those searches have been going for several decades. Here we are looking for a heavy particle of about the size, the mass of the average mid-range nuclei, about something of 100 GeV to a few TeVs. And so far they have not been found. Those particles could also be produced at Large Hadron Colliders, and they have not been produced either. So one alternative which quantum sensors and various quantum devices can probe is ultralight dark matter. Ultralight lies here and somewhere within the range of about 10 all the way 10 to the minus 22, 10 to the minus 25 eV to about 1 electron volt. So anything lighter than 1 electron volt can refer as ultralight. Since we don't know what dark matter particle is, this is just as viable candidate as the WIMPs are. And there are many interesting new physics which can come out which produce and predict those ultralight particles. So the first thing to know about the ultralight particles, that if the dark matter particle is less than 1 or about 10 electron volt, it has to be bosonic. If it were a fermion, it would have escaped long time ago, and our galaxy cannot be bound by fermionic light dark matter, because escape velocity in our galaxy is about 530 kilometers per second. Fermi velocity for such dark matter would be actually higher. So, and the second thing, that if you have dark matter which is bosonic and so very light, then it exhibits coherence, because you run into the issue of having a large occupational numbers of the dark matter by the de Broglie volume. So in a single de Broglie volume, you're going to have a large number of those dark matter particles. So the wave functions actually significantly overlap, and the scalar dark matter exhibits coherence and behaves like a wave. So unlike those WIMPs, you no longer actually detect the dark matter as one particle scatters on nuclei, another particle scatters on nuclei, and now one more particle scatters on nuclei. You detect actually interaction of normal matter with a coherent, essentially classical wave. We have plenty of this dark matter to detect. Our sun is somewhere like right there. And here you see this is our luminous galaxy, visible luminous galaxy. And the dark matter is a very, very large halo, spherical or more likely elliptical halo around our dark matter, around our normal galaxy. And in this picture, for all purposes, we can think that dark matter is not moving on average. So dark matter is virally supported. So in principle, there is a random distribution of velocity, and they are cold, so about 300 kilometers per second. But on average, we assume the dark matter as a mass is not moving, but we, however, do actually move around the galaxy, because our sun and the Earth moves around the galactic center with about 230 kilometers per hour. So think about dark matter as a wind. So as we move through the galaxy, the dark matter comes at us. So that's what we actually detect, this dark matter wind. There is a little bit seasonal variation because Earth also moves around the sun. There's about 7% variation in amount of dark matter to detect between the June and January. And how we would search for dark matter with atomic clocks? Clearly, we can only detect dark matter with clocks if dark matter affects the atomic energy levels. And not all of the types dark matter would affect atomic energy levels, but some types of the particles, for example, the scalar dark matter particles, will actually shift atomic frequencies. So this barrier frequency will now shift and it could shift in a very different way. So the main question we want to answer, what types of dark matter you can detect if you can measure the changes in atomic and nuclear frequencies, and practically you would actually detect changes of frequency ratios to, well, being optimistic, 19 or even more digits, where we hope the clocks would be in near future. Now we can actually switch to clocks. The clocks on GPS satellites are based on microwave transitions. And the microwave clocks have actually extremely progressed since the times of the GPS, but the progress with microwave clocks ended at about now 10 to the minus 16, and it's technologically really not feasible to improve microwave clocks much further. The optical clocks, however, increased tremendously in the past 20 years since the, of course, invention of the frequency comp, because frequency comp is required as an optical clock part because you actually need to measure frequency. You need to be able to count those optical frequencies. As you see now, we are at about 9, 10 to the minus 19, and there is really no technical reason why this progress will not continue for many orders of magnitude more. Just to put things in perspective, present optical atomic clock at 10 to the minus 18 accuracy will not lose 1 second in 30 billion years, more than the lifetime of our universe. So those are extraordinary devices. And there are many applications of atomic clocks, of course, besides the dark matter searches, besides the GPS, tracking deep space probes, definition of the second. You use clocks to synchronize very long baseline interferometry. If you see in the picture of the black hole, that's how that was obtained. Relativistic geodesy, measuring the Earth's geode. The clock, which is sensitive to 10 to the minus 18, can actually detect 1 centimeter in height. It's about 1 centimeter. And then you can use it as a gravity sensor in the future. Also, especially if your clock is 3-dimensional, that is an excellent quantum simulator as well, because you can already, there is a clockadrilla at quantum degeneracy. And this is also an excellent device to study various quantum effects. And of course, the topic of today's talk, to use it to search for physics beyond the standard model. Just a very brief introduction of how optical atomic clock work. So there are essentially 3 parts. So you have your atomic reference. This is your ion. If all the ion clocks now work with still single ion. So it's either your single ion, which creates your frequency reference. This is your transition. And for all purposes, you can think about it as a qubit. This is actually have all requirements of qubit. You actually, as a state, has to be metastable to make this transition very narrow. And in the case of neutral atoms, you could have a few thousand atoms in there, which all sit in optical lattices. So this is cold and trapped. So this is your atomic reference. And what you want to do, you want to build a laser, which is exactly at resonance with this atomic reference. So you have your laser, which is approximately right frequency. You shine your laser at your ion or your neutral atoms, just as much as you actually do to make the 1 qubit gates. And then you see whether the atoms made the transition or not. So what you actually measure is the population of your atoms. And of course, you make it many measurements, many times. And after a few measurements, you adjust either up or down, and you move along those curves to actually eventually get on resonance. So after all the survey and adjustment procedures, you want your laser to be as possible close to the actual resonant frequency. And as soon as on resonance, then you lock your laser and you measure the frequency with a frequency comp relative to cesium clock or to some other clock. And you don't actually have to measure relative to cesium. You can perfectly well connect another optical clock to your optical frequency comp and get the ratio of those frequencies. And that's what's important for our dark matter searches here. Now, just in a little bit more detail how the clock actually works. This is a Ramsey scheme. And again, that looks very much in part as operations, rotations on the block sphere. That's what it is. And that now brings us to the issue of the quantum projection noise. So first you initialize your ion or your atoms in state 0. Then you apply power over 2 pulse, which makes the transition to 0 plus 1 over square root of 2, and then you just wait. And the great thing about waiting is that you don't constantly interrogate your atoms with laser. Right now the laser is off, and then after a while, you bring your atom back down. So you apply another pi over 2 pulse. Actually, those 2 pi over 2 pulses, they are rotation in around the different axes of the Bloch sphere. So here, after pi over 2 pulse, you still actually end up in 0 plus 1 over square root of 2, because that's how actually best to adjust the phase of your laser, and you make a measurement. And of course, as we know, if you make a measurement, what you do, you detect a fluorescence, and the result you should get is either 0 or 1. So that's an issue of the quantum projection noise with clocks. Again, just with quantum computing, you make a measurement, you get 0 or 1, and you have to repeat it over and over again to get this probability of excitation to actually tune your laser to exactly the right frequency. And with dark matter detection, it's important how long this wait time is. And in principle, if you just do metrology, if you just need the best clock stability you can get, you want to wait as long as possible, because your stability is inversely proportional of 1 over square root of the wait time. The problem why you can't wait indefinitely is because while you're waiting, your laser no longer talks to your atoms. Your laser can go off phase while you're waiting. That's actually why you need extremely coherent laser, because laser should be able to remain in phase and on the right frequency while the atoms are actually in the superposition. And there are many different interesting, essentially quantum algorithm schemes of, for example, correlative spectroscopy measurements of how you can actually improve upon that. But the main idea that for the clock performance, you want to wait as long as possible. But for the dark matter detection, you don't want many dark matter oscillations happen during this wait time, because those will be smeared. And then, of course, you can apply different kinds of pulses. So the actual clock operation is very important to the actual dark matter detection schemes. So now, if fundamental constants change, and the dark matter, ultralight dark matter will actually drive the change in fundamental constants, such as constant alpha, which is a fine structure constant, then the frequency shifts. And the frequency shifts, that's what you can detect. And also, despite the fact that technically most of those things except the gravitational wave detection can actually be phrased as a dark matter search, but you can also set limits specifically on actual variation of fundamental constants. You can search for violation of Lorentz invariance, you can test the equivalence principle, and with some improved clock performance, hopefully in the next future, you can even actually have clocks which is sensitive to gravitational wave detection. You can also look for the signal which is correlated with LIGO. That will not be the dark matter signal, but actually there could be additional dark matter signal which spreads relativistically through the system, which is correlated with LIGO. That's another new idea. So how do you detect ultralight dark matter with clocks? So let's go through the steps of the procedure. You now have a dark matter field, which is your cosine wave. It will couple to your electromagnetic interaction, at least we hope it's going to couple to electromagnetic interaction, and your atom constituents, the electrons, neutrons, protons. So you're now coupling your oscillating wave to your normal standard model Lagrangian. You can couple as a different type of portal. The easiest thing to just multiply your dark matter field to your standard model Lagrangian. What it does, it makes fundamental constants oscillate and also mass ratios oscillate. And then the next stage, if those things oscillate, atomic and nuclear energy level oscillates, therefore the clock frequency oscillates. Therefore, if you monitor ratios of clock frequency, one clock sensitive to the effect, another not sensitive to the effect, or you can actually monitor clock to cavity comparison, that's what actually carries this dark matter signal, which you can detect. Just in a little bit more detail, here are your standard Lagrangian. This is the electromagnetic tensor, this F menu term we all know and love. Those are your photons. If you dark matter couple to photons, it just does it directly. And that creates an addition to the standard model fundamental constant alpha, which is also now oscillatory. So dark matter field oscillates, and then therefore your clock oscillates. And of course, an important question, with which frequency will it oscillate? And that depends on dark matter mass, because as you see, this is your dark matter mass here. So if your dark matter mass, it's about 10 to the minus 15, the oscillation is about 1 oscillation per second. And 1 second is a kind of reasonable Ramsey time. So that's actually a reasonable scale for the detection with clocks. At the 10 to the minus 21 in heaviest, in the smaller scales, we are talking about 1 oscillation for over a week. At this point, at 10 to the minus 6 hertz, that's 1 oscillation per 11 days, which is also a reasonable measurement time. So what do you actually measure? You measure the ratio of 2 clock frequencies, and that gets you the result as a plot of the coupling of dark matter and normal matter versus your mass of the dark matter. So how would that actually work? Let's say now you have a standard clock measurement protocol. Let's say you have an ideal clock or a 2 clock ensembles. There is no dead time. So there is no wait. You can make measurements continuously. Here's your 1 second measurement with about a second, say, Ramsey time. Of course, you need very good short-term stability for it. And then your detection signal is going to be a peak at the specific frequency. So you take your time sequence of your frequency ratio measurement. You do discrete Fourier transform. And now in the frequency domain, you should see a peak, which is actually slightly misshapen here, with about q being 10 to the 6, because the dark matter velocity spread, it's about 1/3 c, 10 to the minus 3 c. And that frequency should appear in all different clock comparisons. So it's actually a very specific detection signal. A few things have to be taken into account. If you don't want to smear your dark matter oscillations, you should not have more than 1 dark matter oscillation actually here. In fact, it's best to actually have 1 oscillation with about 4 or 5 measurements. You can actually apply extra dynamic decoupling pulses. If you apply extra pi pulses, you could actually measure with several dark matter oscillations per the wait time. And you should have at least 1 dark matter oscillation during your entire measurement time. So, and that actually what sets which dark matter masses you are sensitive to. So those are present scalar DM limit. Those actually, the limit on top of the graphs come from microscope mission. That's a classical mission in equivalence principle mission in space. Those limits are clocks. The green line is rubidium cesium clock. The red line is dysprosium. And I haven't yet plotted the new result from JELA, which is of course below here. And there are, I know, a number of dedicated experiments which are ongoing. So the important part, how we shifted down, and also how to be shifted to the high masses. That's what we are working on now. And just to, I would like to point out, those were oscillating type effects. You technically could also have a transient effects, which was suggested in 2014 by Derianka and Pospelov, that you could have topological defects of various kinds, and those would be also ultralight dark matter particles, but which, you know, cluster in some way in the large scale, and large scale, I mean Earth-size scale type of structures. And those could be detected with networks. In this case, the best limits come from recent measurements with global sensor networks. And there have also been measurements done with the GPS. And here you actually look at the correlated signals between your network. So the important question, how do we now improve upon that? This is all of this, it's a very new idea. All of those new papers which started all those searches are only about 5 years old. So of course, the first question that you can improve, well, by improving the clocks. And the interesting question is how far down this rabbit hole goes. And there's no reason technically why we couldn't improve those hopefully soon, in maybe 5 years, by another order of magnitude, and then improve further. But then there are many new ideas how to improve stability and uncertainty, have more ions, ion chains, large ion crystals, have also operating 3D optical lattice clocks, also measure beyond the quantum limit. This is going to be very large thing, I think, in the next 5-10 years, and also use entanglement in ion clocks. And then the other idea is to use different clocks, to have clocks based on new system. For example, have now clocks based on a nuclear transition, not atomic transition. Well, unfortunately, there's only one nuclei, which actually has transition within possible laser range. It's actually this now, it's 150 nanometers, and that's transition of thorium to 29. This is a nuclear transition at about 8.2 electron volts. And the other possibility is clocks with highly charged ions. I know there have been great Pete Schmidt seminar, it's quantum science seminar number 18. They've been the first demonstration of quantum logic with ultra cold, highly charged ions. Here what you see is actually a large argon 13 plus ion, and you can see how large that thing is because it's 13 plus embedded in beryllium plus crystal. And here is a quantum logic with a single ion. And the reason why we want to do those novel clocks, it's because of sensitivity to all of those variation of fundamental constants and dark matter effect. And sensitivities actually determine that if you determine the ratio of frequencies, how does it translate into variation of alpha? So there is additional coefficients, and most of the current clocks have actually very weak sensitivities to this effect because electrons in those clocks, which are probe electrons, are actually highly non-relativistic. So the largest factor is ytterbium E3 with a factor -6. We have another proposal with a ytterbium neutral clock, which will be about -15, but that have not been yet done. Cavity would also can be used with effective factor K being 1. If you're interested how that works, then let me know, I can explain. So the interesting part about those new clocks, it's much higher sensitivity. So for the nuclear clock, sensitivity can be as high as 10 to the 4, 10 to the 4, 10 to the 5 orders of magnitude higher than for the atomic clocks. And that's one of the attraction in building this very difficult task of building the nuclear clock. And also that the nuclear clock is actually sensitive to variation of strong interaction coupling constants rather than electromagnetic. So it couples dark matter to different to nuclear sector of a standard model rather than electromagnetic one. And the reason why sensitivity is so high, because with a nuclear binding energy at about GeV scale, the difference in the Coulomb energy is estimated to be in some way MeV or large keV scales, but the actual transition is at EV scale. And the variation of alpha sensitivity comes about from the ratio of those two effects, and that's about 10 to the 5. There is an effort to actually establish actual enhancement more or less to the high accuracy. And the other thing that the dark matter will couple differently to a nuclear clock because it will also come to gluonic sector, it will couple to quark sector. And it's really very advantageous to some of the particular dark matter models to be able to couple to quarks and gluons. For example, one model we considered recently with Gilad Perez's group at Weizmann Institute is looking at the thing called a relaxion. The relaxion, it's a very interesting solution to the problem which is called a hierarchy problem. Why is a weak interaction so much stronger than a gravitational interaction? This is actually very unnatural in the model of our universe. And it actually provides an alternative explanation, and the one explanation of that effect will be provided by supersymmetry, which is looked with a large hadron collider. But it's possible that actually there is no heavy particles which contribute to this explanation. It's all actually done by ultralight particles. And the main actor of this cosmic relaxation scenario is a relaxion. It's a light spin zero field, which then allows the Higgs mass to be small and also could be detected with a nuclear clock. And here is a potential nuclear clock reach, and it just goes essentially inside of the potential relaxion parameter space, and pretty much for the ultralight relaxion, no other device can reach the parameter space of this particular particle, and we are continuing collaboration with Gilad Perez's group to look at that. In the lucky instance that relaxions actually cluster around Earth or Sun, which is potentially possible, then the nuclear clock would actually be well within this green line within the sensitivity with the potential parameter space. So this is actually a nuclear clock would be an extraordinary device to search for dark matter. So I was asked to stop at some point about halfway through the 1 hour talk, which I have about maybe 10-15 minutes more. And I would like to switch to progress in atomic theory, but perhaps maybe the questions about dark matter can be asked first. So
Yes, Marianna, we collected a few questions. Let me start with a question that appeared twice, and let me read Bill Phillips' version. Do I understand correctly that you don't want WIMPs heavier than the Planck mass because they would be black holes, and such small black holes, are they not good dark matter candidates? Why are such small black holes excluded?
Well, because there are actually limits. So now, if as soon as we go into black holes, we go into total different scenario for the dark matter. Because for a long time, there's been another scenario for dark matter I haven't mentioned. The dark matter is not really a single particle in the first place. It is actually a black hole. And the normal black holes have been excluded by various those microlensing experiments. But there is another scenario, and that's why those black holes are excluded. It's because it's possible to make black holes without ever having stars. Because usually we think black hole, you have a star and then you end up with a black hole. That's actually not the only way you can end up with a black hole. You can actually have primordial black holes, which actually have been produced very early in the universe. And there are limits on those primordial black holes. And those very, very small primordial black holes would evaporate by now due to Hawking's radiation. That's the one thing. But the heavier, like not like a Planck scale black hole, but a bit larger black holes, but not enough to evaporate now, that idea has been tested. And there is it's not excluded yet, but the idea of primordial black holes being dark matter has some gaps. So it's not been completely excluded, but essentially one thing, I think you actually have infall of those black holes into different astrophysical objects. And that is actually not something which we can miss. So this is a very specific signature. But the primordial black holes have not been completely excluded, but having extremely light black holes actually have been excluded. So that's so why in principle black hole is a viable dark matter candidate still, but within the next 10 years that could actually be excluded. In fact, at this point, the black holes will have to actually cluster in some way to be dark matter. So that's been very actively researched before. So I don't have slides, unfortunately, about primordial black holes, but it's a whole large topic of research. But for particles, we kind of have to stop just short of that. Also, it's very hard to produce such dark matter. You can produce primordial black holes, but producing those WIMP-zillous, very, very heavy dark matter, you can produce them gravitationally, but it's non-trivial. So that's why normal WIMPs at few TeV-ish scale.
Okay, thanks. And I want to ask two more, actually. So one was asked on the chat, and that's a question, if dark matter is around us, how come we are not just feeling its effects due to gravity?
Oh, remember, for the dark matter density, it's about 1 atom of hydrogen per few cubic centimeter. And one time I was actually sitting at some point at some conference and thinking, well, every once in a while people say the dark matter is this elephant in the room. And I was just wondering, do you actually get an elephant on dark matter per Earth's mass? So if you compute for the scale of Earth, how much dark matter in this volume you would have, you have about a kitten, a small kitten, about a few hundred, 100 grams of dark matter. That's why there is just the dark matter density is very small. It's just that dark matter extends so far outside of our galaxy that the total mass of dark matter is very large comparing to our matter. But the dark matter mass in our solar system, it's essentially negligible in comparison to actual normal mass. There have been papers, if anything even interesting, I can actually send you the link. There have been papers on which actually set maximum mass of dark matter between the Earth and Moon orbit. And those are done from laser ranging experiment, because laser ranging experiment tests gravity between the Earth and the Moon, and we know exactly how much dark matter mass we can tolerate. And this is by far a larger thing that's actual estimated mass of the dark matter if the density does not have any clustering around Earth. And that actually sets a limit of how much dark matter could be clustering around Earth for whatever reason, the laser ranging.
Okay, so one last one in now midterm. a bit more technical. You had this interesting slides about the strength of the effect basically on the frequency ratios with your constant K, right? That was your scaling. Yeah. And the question is basically, so how does it happen that a cavity is at K equals 1?
Oh, let me go back. This is actually very interesting. Okay, so first, it's not just any cavity. This is very special, a silicon crystal cavity. So now you actually have this crystalline length. And this, so what happens to so we know what happens to the atoms when you have this oscillating dark matter. And the effect of proportionality, don't forget that when we say that sensitivity of strontium is 0.06, it is actually only relative to other clocks, because all of the atoms would also have an extra sensitivity of 2, because all the Rydberg constant proportional to alpha squared. And all atomic frequencies scale with Rydberg constant. So technically it's not 0.06, it's 2.06. Now, what actually happens with a cavity? So when the cavity is now in this dark matter oscillating field, so the scale, the size of the cavity now will change with the Bohr radius. And then you have a proportionality of not alpha squared by alpha. So now you have atoms which sensitive to alpha as alpha squared, K being 2, and the cavity which is sensitivity is alpha, being now as a power is 1. So 2 minus, so you have essentially K2 for the atoms being 2 and K1 for the cavity being 1, because it's a length which changes when the dark matter field is oscillating. So now the effective result is 1.
Okay.
Because we all forget that there is actually 2 in there as well. So.
Okay, good. Then I think I let you go on and we ask more questions towards the end.
Okay, so now I would like to talk about our recent progress in our group, in collaborators in atomic theory. And generally people say recent, that can refer to anything in the past 20 years. I want to say it's very recent, past year. So what's been happening? First, we found that there is a numerous applications that need precise atomic data. And we're actually fortunate to be asked by very different communities to produce various atomic data. Of course, the clock and various ultra-cold atom experiments and quantum computing. Everyone needs to know essentially potentials. If you trap your atoms in laser fields, you do need to know atomic structure to understand how those atoms would behave. And of course, all of those dark matter and other new physics searches, you need to know how sensitive is your atom to new physics, and not just some weird extra Hamiltonian you put in. Also, extracting nuclear properties from laser spectroscopy also requires atomic physics, and astrophysics and plasma physics have been user of atomic data for ages. So we have been working in creating a very large suite of precision atomic codes and applying them to solve all of those problems. We collaborated with all those communities for the past 20 years. All codes are written by us. And because we have several ab initio codes, we can estimate how accurate the numbers are. So we routinely actually put error bars in our number and know this is not statistical or systematic uncertainty. This is actually sort of our best guess on 1 sigma. With sigma being that if this actually is measured, we hope that will be about within 2 sigma, sort of, from our numbers. And we generally so far have not really been seriously wrong every single time in any of the cases. We also have codes which write formulas, we have codes which write codes, and of course there's so much data, we have codes which analyze data. We have pretty large resources. UD has about 10,000 cores cluster. We need enormous amount of memory, and we're talking about 12 terabytes of memory to run our codes for some of the more complicated systems. And essentially at this point, we can compute atomic data, very broad range of atomic data, the structure data, for any atom ions with from 1 to about 5 or 6 valence electrons, and that could be neutrals, singly charged, highly charged, or even negative ions. So that's our present capabilities. And there've been enormous effort to actually increase the reach of our methods in the past year. So we now have a new parallel version of configuration interaction code done by Charles Cheng, the student in our group. And we can actually now run 100 times larger problems. And the first thing we tried a new code on, this is a recent paper. It's a famous long-standing 3C3D problem. This is astrophysics problem, not ultra-cold problem. This is an iron 16+, that there were 2 oscillator strengths, their ratios was measured, And that did not agree with experiment between theory experiment and astrophysical observation for about past 40 years. And this is just 10 electrons. We were able to correlate those 10 electrons exactly. Usually there is some effects you want to include. Okay, maybe those excitations and maybe this basis. We were done. We essentially had no other ideas what we can include. We still don't agree with precision experimental colleagues. So experiment 309, we have 355 plus minus 5, and this is the remaining puzzle, but we are really sure in this last 5 here. So we have a data at about the % level for the ratios, and our uncertainty for the energy, essentially it's below uncertainty of the NIST database right now. So that was the first thing. The other thing, it's a very complicated system. For example, Jose Crespo's group has a spectrum of iridium 17 plus, which had been suggested for clocks. It has a very large enhancement of the variation of alpha. It's a very complicated structure. You have this 4F14, 4F13 5s, and 4F12 5s squared. And essentially various calculations couldn't have difficulty predicting range of the clock transitions. And the one important point that from the FAC calculations, they should have seen those weaker one transitions, but they did not. And we actually explained why they didn't. We had this first ever configuration interaction, which included correlations for all 60 electrons with all shells open. And we're talking about hundreds, millions determinants here. And we found that if you actually include the extra shells, those rates are actually incorrect by more than a factor of 100. And this is below the range, the sensitivity range for spectrometer. We actually predicted which transitions actually could be observed. And now we have a new computation, since now we have our new extra memory, to actually get a spectrum for all strong E1 transitions. And unfortunately, there are really lots of them. So this is actually a very nice exercise from quantum mechanics to all the students. Compute how many configurations there are in 4F12, 5S5P, and I'll go give you like 5 seconds to think just how many. Well, you can't really tell, except this has to be a large number. It's 138 levels. There are 138 levels in this one configuration, and we computed all of them. So at this point, we can actually compute things in bulk, in very large numbers, and that's something we absolutely could not have done before, and hopefully we'll actually be able to identify the entire VUV and EUV spectrum here with the new work. Then another work in collaboration with Pete Schmidt. It's actually very complete assessments of the californium ions for clocks. Yes, californium is not stable, but it is a very long-lived, and after all, your clock only needs 1 ion. So it's actually a very viable idea for the clocks. I know actually there have been people, some received some funding to actually look at the californium for clocks. And here, if you actually compare those two ions, your sensitivity factor is 110. It's very large. And then now I will talk in the last 5 minutes about our completely new project. It's about 1 year old, and we already have something to show. So our idea is that so many people need atomic data. Somehow we really need to solve this problem. The idea is that we would like to compute everything which could be computed with our code, should be computed and put in a searchable database online, and people should be able to request what other stuff to compute. So the idea is to actually move from our sort of prototype physics codes to actual software. And that software, it should not be as a code which you download, and it takes you months and months to understand how the thing works. We would like that it to be trivial how to use those codes. And we would like to actually pre-compute everything which we could with those codes as well. So when I said trivial to use it, meaning that you should tell the code essentially what you tell me if you send me an email that I want, for example, a matrix element of cesium from 7s to the AP1/2. And that's what you tell the code. You essentially input just what electron you want and what property you want and what element and isotope you want. And that should be all the input. Everything else is buried in the code. You don't need to know what it is. And just to put things in perspective, we divide all the computation by the difficulty level in a very different way the experiment does. So for us, it's not the wavelengths of the transition. For us, it's how many valence electrons we have. For example, cesium does have those 54 electrons in closed shell, But honestly, we mostly care just that the fact there's only one valence electron, which is not as actually in any completed shell. And for us, computation of sodium and cesium, it's basically the same computation. Computation of cesium and barium is not the same. So we could divide all of the atoms in the periodic table by difficulty level. Group 1, stuff we can do routinely, all of that is going to be on the portal. It's 1, 2, or 3 valence electron. 1 is totally automated now, 2 or 3 are not, but will be in about half a year. Then the next group, computation which require expert knowledge, meaning you can't include sort of everything by its default factors, but you can actually write a code which does it. So only computations of wave functions require initial expert knowledge, but as soon as you have wave function, any matrix elements can be computed with them by anyone. And we will actually have wave functions stored. And then the next group, which really have such a severe issue with exponential scaling, because remember, the scaling with the number of electrons is exponential. This is exactly the same issue as simulating the quantum computer. As soon as you have more than about 30 electrons, essentially it's extremely difficult. And in our case, we are happy to have a mean field. So as long as you can do mean field calculations first, that's good. But for many of those computations, that's not enough. And you actually have to do exact configuration interaction between many, many different shells. So those half-filled shells, half-D-filled shells, half-F-filled shells. I just showed you example of this iridium-17 plus. We essentially just starting there. We have a funded project to find out how to do it. Most likely, we actually need to have machine learning algorithms which select the configurations. And that's sort of a completely new projects which you do have. And now I would like to show first our level of automation. Monovalent system, that's how the flow chart for the codes work. I say computer, calculate thorium 3+. It computes the basis sets, it computes the couple cluster core. By itself, there is essentially batch script which does everything by itself. Only thing you need to input which isotope. For now, you want to tell it what core is. I couldn't even take that out. Which electronic states you need, and you can say, okay, I need first 60 states or first 10 states of each partial wave, and which properties you need. If you want E1 transitions, you just say all E1, and that's it. There is essentially no other inputs. And it will just give you a table actually in LaTeX with all the results. So that's been completely automated. And now I would like to switch to show you the portal. Portal is not yet an open access for now. Let me switch. So can you see my different screen, Sebastian or someone? Can you see the portal screen now?
Yes, yes.
Okay, so graphic design not yet done, so there are, it probably will look differently eventually. But what we have now for 12 elements, and yes, we will have strontium, calcium, and others soon, but not yet. We have matrix element, transition rates, polarizabilities, and eventually be other data like you can request E2 and 1 transitions, hyperfines, and maybe alpha variation sensitivities and other. It's not functional yet, but those 3 are. For example, if I click on cesium, you get all those states. So we have data for all of those states. If I click on 6s1/2, this is all reduced matrix elements to the point of functionality of our codes. We put atoms in a box, so we can't make box infinitely large. So we're about to end about 14, okay. We eventually have idea to have a separate stuff for Rydberg atoms. That we don't have that yet. So all of the data are from theories, there are uncertainty estimates for everything. But if there is an experimental measurement, which is super accurate, then actually experimental number is put in, and you can click on the reference and see where that actually comes from, and click on get a DOE page for the paper. So if you look at different atoms, and wavelengths just come from this database or from theory if it's not available. We don't list very long ones, but we could. So, and then actually that gives you all the various transitions which are allowed. If there's more than one extra reference, you can get a couple. So now that's for reduced electric dipole matrix elements, but we understand sometimes it's easier to directly have transition rates and people are interested in lifetimes and branching ratio. So this is a different page. Again, let's look at cesium. Now, that's a 7s lifetime. There are only 2 transitions which contribute, matrix element wavelengths from NIST, transition rate and the branching ratio. Here, of course, you have much more transitions. And again, the lifetime. All data can be either printed or downloadable as an Excel file. And also, if you just want every transition rate for cesium which has been computed, you can click on all, and you can get the entire table. Again, that's searchable and downloadable. And for astrophysics colleagues, also the request was you can actually order by the wavelengths, or you can order by the transition rate as well, or you can just search for a specific electron. So now the strongest one, of course, would be 6s, 6p would be first. And now if you go polarizabilities, there are dynamic polarizabilities. For example, this is graph for the 6s, 6p, 7p. We decided that would probably be sufficient for traffic purposes. And you can actually scale the graph. And if you need a specific region, or for example, you can actually just have graphical tools. And when you download this, you will just download the part which you want. You can actually combine graphs together. This is the differences between 6s and 6p. And yes, there'll be a list of all the magic wavelengths and all the magic zero wavelengths. They're not yet there. You can actually turn the graphs off and on. So there is an additional graphical tool. And yes, we will have all of those for alkaline earth as well in the next release. So I'm going to switch back to the talk. So the portal we have, as you see, all the transition, E1 transitions, it will also have E1, E2, and one matrix element. Technically, we have almost more than 15 different matrix elements our code can compute. It can calculate the parity violating stuff and T violating stuff as well if needed. We'll have dynamic polarizability, magic wavelengths. We'll have computations on the fly. Uncertainties be provided. We'll have code releases, tutorials. Codes actually will be released. Actually, source codes will be released for everything. And we actually would invite guest scientists to come to us and learn how to use Portal, how to use all the codes. And we will seek to establish future international collaboration for the Portal. And we plan to release the first version next month. It's almost, as you've seen, it's almost ready. All the data already exists and just being put in. Everything is automated. And alkaline earth, it's the next stage. We don't have codes fully automated for the alkaline earth yet, but we will. And we hope to have about 30 atoms maybe within the next year and then extend it afterwards. So email me which atom ions data you would like to see included in the portal. So in summary, atomic and nuclear clocks have a great potential for discovery of new physics. Many new developments come in the next 10 years. And we really also need more new ideas how to use quantum technologies for new physics searches. So we have programs of collaborating with particle theorists on actually how to progress even further. And I would like to acknowledge all of our University of Delaware people, our online portal collaborators, and our experimental collaborators. And know that we have a senior research associate position for those already with postdoctoral experiments available now. The search is ongoing. And we'll have another postdoc position become available in January. Contact me for more information. Thank you so much for your attention.
Yeah, thank you, Marianna, for this very interesting talk. And maybe I start, basically I have one question so far for the second part. Let me ask this first. That comes again from Bill. And that is basically about, can you give us a feeling for why including all the correlations between the electrons makes all of those E1 transitions of this highly charged, I think it was iridium 17 plus, right?
Yes.
Smaller by 2 orders of magnitude. So what's the physics behind it?
Oh, that was actually extremely interesting. So what the previous computation did not include, they never allowed excitation out of the 4p shell. So, and if you look at those different transitions, what actually the transitions we allowed will be either F to D or S to P, and they between different mixed configurations. So, and when you have S to P, if you don't allow excitation out of the 4p shell, then anything which is like 4p to 5s is not allowed to contribute to your many electron transitions. So this one electron transition from the inner shell was not allowed to contribute. And it's because it just takes enormous amount of computational resources to open a 4p shell, because even with a 4d and 4f, you already have 24 electrons. Opening the 4s and 4p, it's another 10. So no one have done that before. So we actually tracked down exactly what made the changes. Those are already very weak transitions. So we found that there is a very large cancellation which occurs if you include those additional channels. So this is a problem of insufficient computation, that just not enough contributions to those many electron transitions were actually computed. And that's been tracked down to specifically 4p shell. The rest of them changed it a little bit. The 3p already doesn't contribute as much.
Okay. So then we have quite a few more questions, more general, and to the first part. One from Roman Bause by email, which is, why is it reasonable to expect that ultralight dark matter should interact electromagnetically, since the interaction would have to be extremely weak, such that we have not seen it until now? And electromagnetic interaction, on the other hand, is usually very strong. So this seems like an unlikely choice.
First, it couples to electromagnetism, but it doesn't really, when we say that it interacts with the electromagnetic part of the Lagrangian, it doesn't actually interact through the photons. So the coupling is not via the photons. The coupling is through the unknown mediator. So the idea is that you have this E&M term, and you have, which is standard model part, and then we have that dark sector part, and they're actually not interacting through the electromagnetic interaction. They're interacting through an additional unknown mediator, which could be very weak, and that's why we haven't seen that before. In principle, I think the scheme which is the easiest to understand, it's actually a vector scheme when you're actually interacting through what's called a dark photon. Because a dark photon, the idea that the normal photons have actually very small admixture of this dark photons. This admixture is 10 to the minus 10, very, very small. So the dark sector interacts through the dark photon part, but then there is a small admixture between the dark photon and normal photon. So now you have dark photon starts, and you have now normal photon, and that part couples now to your normal standard model. So there are several of those what's called portals. So you can actually do it through the spectra, through the photons, and you can do it through the Higgs, relaxation couples through the Higgs, and that allows you to couple to actually different parts of the Lagrangian, or you can actually couple through the through neutrinos as well. So the coupling itself is not electromagnetic.
Okay.
That's why we don't know how weak that is.
Yeah. Okay, then two questions, basically to the dark matter searches with atoms, so first part. So one is, can you distinguish actually the effects of dark matter on atomic frequencies from other physics? For example, like the Lorentz invariance violation that you also had in your talk at one point, right?
Right, so the Lorentz invariance, the effect which is visible with atoms is tensor effect. And also the periodicity is different. So here, if you have oscillatory effect, then the signature actually appears at a very short time scales. Lorentz invariance would actually be sidereal or semi-sidereal. So the variation with a half, with a Earth day or with the Earth year. So you can actually, you can fit into different type of oscillations. If your dark matter conspires to accidentally have correct period, that would be difficult to determine, but that's kind of, unlikely. So in this case, you could distinguish Lorentz violation from the oscillatory effect. Transient effects actually look completely different, and they definitely can be distinguished from Lorentz violation. Also, Lorentz violation, you have different terms, and again, it's a period of the variation which you actually would be different. And also there will be specific, you can definitely distinguish Lorentz violation signal. You could also distinguish signal when dark matter directly couples to the gravitational potential, when there is a periodicity with the Earth, with the sun gravitational potential change, because that is also changes with the year, but it's not, if the effect is different from the Lorentz violation. So yes, you could actually separate those well.
Okay, great. There's another question that was actually asked in different flavors twice. And that's about the nature of those oscillations of the frequency ratios or of the atomic levels. Can I think of these oscillations as being an indication that somehow our familiar states are not eigenstates, as with neutrino oscillations, for example, where the familiar neutrinos are not eigenstate? If so, what are actually the eigenstate, and why are they not the things we see? And then that was a question from Bill. I have to read the last part. Does the question even make sense?
Well, this is actually different from neutrino oscillations. So let me go back. So what we have here, and okay, so dark matter field. What we have here, we don't really have different quantum states. We actually have a relatively simple picture. I think I actually have it in pictures somewhere. Okay, first, that could be more complicated, that there are actually different states, etc., etc. But for now, we're actually not considering it. Yeah, okay. So all we have here is just that you have a lot of those dark matter particles with fairly extended de Broglie wavelengths. And excuse me, and so you have a dispersion because of the velocity of the particles, but also if you actually you have a wave which oscillates at about, you know, let's say 1 second. So the coherence length is actually pretty large in this case. It's well within, you know, time scale of your experiment. So here we are not talking about having certain eigenstates of your dark matter. It could be perfectly just a single dark matter particle. What important is there are a lot of those dark matter particles. There could be, you know, 10 to the 15 those dark matter particles in a single de Broglie volume. So what we do, we simply look at those particles. They exhibit coherence behavior. So they're not actually eigenstates of different particles. This is just simply having sufficient overlap with the wave function that all of those no longer behave as individual particles. So that's all it is. It just simply is a classical wave issue, and that we, for the purpose of the detection, its interaction considers as a wave. So we don't have a different eigenstates here. So those are not oscillations between different states of the same particles. That just simply the amplitude fluctuates. And then, of course, if you actually put dark matter decoherence and how it fluctuates, it will become much more complicated afterwards.
Okay, so I have one final question, and we'll refer the remaining ones to the chat later. And that is, if the dark matter search fails to find anything, what is actually then ruled out? Or does it actually push down the interaction strengths that remain as free parameters? That was also from Bill.
Yeah, it's very, very, well, look, I think we will definitely enough work. Let's say I very much hope that we're lucky and we find something soon, but the parameter space is large. So some things, if we don't find, for example, some things like WIMPs and axions by themselves could pretty much be ruled out eventually. And that's hopefully could actually, either they will find them in our lifetime, I hope, or because WIMPs and axions are needed to solve other problems. The WIMP problem, the hierarchy problem could be solved by relaxation, which is not heavy but light, and then just supersymmetry doesn't exist, for example. So ruling out the dark matter as a particle completely, it's not feasible within any foreseeable future for the one simple reason. There could be a really bad scenario when it actually does only interact gravitationally, that it actually does not talk to standard model any other way. So why is it unlikely? Because somehow this dark matter was produced, and somehow it was produced through some interaction. And if it doesn't talk to standard model through any interaction except gravity, it has to be produced gravitationally. And most of dark matter cannot be produced gravitationally. For example, WIMPs can only be produced thermally. WIMPs have to talk to the standard model, period. So, and so do axions. Axions have to talk to standard model particles. And there is a very specific band. If you don't find a QCD axion, the strongest problem have to be solved some other way. For the dark matter in general, again, it's possible that it's been produced gravitationally and it does not have a standard model interaction, but that's a fairly unlikely scenario. So completely ruling out dark matter, that's not going to happen in the nanocentury. I really hope that we'll find what it is soon. But if we don't find what it is, unfortunately, there's too many possibilities of what it still could be.
Okay, Marianna, thank you again on behalf of all the listeners and watchers for this great seminar. And I hand over to Sebastian.
Yeah, thank you, Marianna. Also from my side, I'm really looking forward to that database. This is going to be super useful. Next week on November 19th, we will have yet another talk by Christiane Koch, who will speak about quantum control with molecules. If you want to get notified of what we do, please go to our website, quantumscienceseminar.com, subscribe to our email list and our Google Calendar there. You can also follow us on Twitter. You should certainly also check out our sister seminar, the virtual AMO seminar, where tomorrow they will have Kanko and me talking about building single molecules from scratch. If you want to join us for a Q&A session with Marianna, please join us in the Zoom session using the link I just pasted into the YouTube chat. Well, thank you for your interest, and we hope to see you again next week, same time, same place. Bye.